When an object is confined to a straight line, tracking its motion is mathematically trivial. You simply assign a positive or negative sign. Positive means it moves one way along the track. Negative means it moves the exact opposite. But release that object into an open plane, and that binary system fails. An object carving a curved trajectory through two-dimensional space cannot be accurately mapped with simple pluses and minuses. To calculate both the magnitude of the movement and its precise angle of direction, we must adopt an entirely different mathematical grammar. We need vectors. In this framework, we track an object using a position vector, denoted as r. It is a geometric arrow drawn straight from a fixed origin point to the object's exact location in the plane. The leap into multidimensional space feels as though it should require new physical laws to solve. It doesn't. Through a process called orthogonal resolution, we can dismantle any complex, arcing two-dimensional path into two simple, simultaneous one-dimensional problems. Moving from a straight line to a two-dimensional plane is an upgrade to our geometric language. The physics themselves remain exactly the same. Visually, we add vectors using the head-to-tail method. You place the tail of vector B at the head of vector A and complete the triangle to find the resultant vector. It is geometrically true, but algebraically clumsy for precise calculation. We bypass that problem with vector resolution. We project a single diagonal vector onto a rigid Cartesian grid, dropping perpendicular lines to form orthogonal shadow components along the x and y axes. To write those geometric shadows as exact mathematics, we need unit vectors. These are vectors constructed with a magnitude of exactly 1. Their sole mathematical function is to point. The I-hat vector points perfectly along the x-axis, and the j-hat vector points perfectly along the y-axis. This notation allows us to express our original diagonal vector as an exact equation. Vector A equals its x component multiplied by I-hat plus its y component multiplied by j-hat. This equation is highly efficient. Multiple complex vectors can now be added entirely analytically by grouping all the respective I and j terms together. Unit vectors serve as a rigorous translation layer, converting diagonal geometry into independent, organized columns of one-dimensional algebra. We can now apply this grid framework to motion over time. An object's position is simply its coordinates. R equals xi hat plus yj hat. When that object moves along a curved path, its displacement is the straight line vector difference between its initial position, p, and a later position, p'. Dividing this displacement vector by the elapsed time gives us the average velocity. Because time is a positive scalar, the average velocity vector points in the exact same direction as the displacement across the gap. But physics occurs in exact instants, not averaged across gaps. We must calculate the instantaneous velocity. We find it by applying a mathematical limit. Watch what happens as we shrink the time interval towards 0. Point P' slides backward along the curve, and the secant line rotates. At the limit, the vector perfectly aligns as a tangent line, touching only point P. That alignment is the instantaneous velocity vector. Algebraically, the time derivative distributes cleanly across our unit vectors. It isolates the rates of change. The velocity equals the derivative of x in the I direction plus the derivative of y in the j direction. Instantaneous velocity in two dimensions is the literal convergence of a secant gap into a continuous tangent flow. We apply this exact same geometric logic to how velocity changes over time, giving us acceleration. Average acceleration is defined as the geometric difference between two velocity vectors across a time interval. Observe an object moving along a curve. Even if its speed remains constant, the tangent velocity vectors at points P, P1, and P2 point in slightly different directions. The velocity is changing. To calculate that change, we pulled the initial and final tangent vectors off the curve and set them tail to tail. The resulting vector drawn from the first tip to the second is the change in velocity. We again compress the time interval towards 0. As the gap closes, the change vector continuously shifts its angle until it locks into a final instantaneous direction, pointing inward relative to the curve. Just as we saw with position, the acceleration derivative neatly separates. The total acceleration is the derivative of the horizontal velocity on the I-hat axis plus the derivative of the vertical velocity on the j-hat axis. Calculus handles multi-dimensional changes effortlessly because the orthogonal unit vectors never interfere with one another. Each dimension operates as its own completely independent parallel universe. Let us bring this theoretical framework into a practical scenario by examining an object moving with constant acceleration. This is the standard two-dimensional kinematic vector equation for constant acceleration. Final velocity equals initial velocity plus acceleration multiplied by time. Recall the rule of our grid. Motion along the x-axis is entirely blind to the y-axis. Because of this rule, our single vector equation splits into two independent one-dimensional equations. A complex movement, like a projectile arc, is nothing more than these straight-line equations executing simultaneously. The horizontal velocity vector remains constant, while gravity alters the vertical velocity vector independently. The only mathematical variable binding these two parallel universes together is the scalar flow of time. We started with the failure of one-dimensional positive and negative signs. We built unit vectors to resolve geometry into algebra, and we applied mathematical limits to find exact instantaneous rates of change. Mastering vectors proves that the universe's geometric complexity does not require impenetrable new physics. It can be cleanly dismantled and understood, one dimension at a time.